Hi, this is Barrett Givens, and in this video we're going to prove this theorem that says that if you have a collection of subsets of X called T, then T is a topology if and only if these three properties hold. So the first property is that the empty set and X are in T. The second property is that any union of sets in T is also in T. And the third property is that any finite intersection of sets in T is in T. So if you are coming to this video from somewhere outside of my class, you might be confused because you might be thinking, wait, isn't this actually just the definition of a topology? Like, how is this a theorem? This is the definition. Okay, in this class, in this sequence of videos, we're using a slightly different definition of topology and basis, which this theorem is basically showing that they're equivalent to the usual definition of topology and basis. So what we are doing is we're saying that T is a topology if and only if every set in T can be written as a union of sets in some basis B. That is our definition of a topology. And that B is a basis if it satisfies these two properties. The first one is the coverage property. So every point in your space has to be inside of one of these basic open sets. And the intersection properties, that whenever you take an intersection of two basic open sets that has a point in it, you can find a third basic open set that contains that point and is contained in the intersection. So these are the facts we're working with. We also have a lemma with certain properties already proven, and that lemma is going to be very useful in proving this theorem. So let's go ahead and prove this theorem, and then that will be nice because then we will have shown that T is a topology if and only if it satisfies these three properties, and that matches up with the more typical definition of topology. And so that means that moving forward, the things that we're going to do are going to match up with what's done in a more typical way of starting a topology class. Okay, so proof. First of all, this is an if and only if, so there's two directions that have to be shown. So let's start with the forward direction. Suppose T is a topology with basis. Our definition of topology is that it has to have some basis, okay? Well, we've already seen via a lemma that 1 and 2 were previously proven in a lemma. So if you want to see that, you're going to want to go look for the other video that proves that lemma. And then 3, for 3, the lemma that we previously proved showed that an intersection of two sets in T is in T. Well, if the intersection of two sets in T is in T, then you can use induction to show that the intersection of any finite number of sets is in T. So our lemma did all of our work for us, which is what we want lemmas to do. Okay, so if T is topology, then by the previous lemmas and properties that we've shown, 1, 2, and 3 have to be true. All right, now suppose that 1, 2, and 3 are true. Then I want to show T is a topology. To show that T is a topology, I have to show that every set in T can be written as the union of sets in some basis. So I have to tell you what the basis is. So let's let my basis be the same as my topology, but remove the empty sets. So basically what we're saying is that every basic open set is basically a non-empty open set. Every basic open set is basically, yeah, okay. i.e., a set is a basic open set if and only if it is a non-empty open set. So would this alleged basis, meet the definition of a basis? And is it true that the topology, every open set in the topology can be written as a union of sets in this basis? Well, certainly every open set is also basic open set. So every open set can be written as a union of just one basic open set, which is itself, okay? So T is certainly generated by B in the sense that every open set can be written as a union of basic open sets. And then secondly, is B a basis? Does it satisfy the coverage and the intersection properties? Well, the coverage property is satisfied because by property 1, X is in T. So X is in B. X is a basic open set. And so every point is contained inside of X. And so we're done. Okay. And then by property 3, anytime you take a intersection of basic open sets, it'll satisfy the intersection property. Okay, so the proof of the theorem was not that hard. That's because we did a lot of work to get to this point where we have all these facts that make the proof of this theorem sort of straightforward. Okay, so this now means that in our class, as we are looking at topologies and bases, we can now use what is considered the definition in most classes of a topology. So in most classes, they start with the definition of a topology being something that satisfies these three properties. And then they define a basis later, and then they show that every basis generates a topology that satisfies these three properties. You end up doing sort of the same work no matter what. But I like this way of doing it, so that's how I decided to do it. Okay, thank you for listening.